don't know why.
Okay, guys, this carbon here. Nitrogen is 1, high priority, highest atomic number. 2. Carbon up here, carbon here. Now you gotta look at what's on the carbon because of the same. What's on that carbon? It has a nitrogen. What's on the lower carbon?
See, that's what, because the hydrogen is going forward in that one.
So we reverse it. It's 1, 2, 3. It's clockwise, which is R. We reverse it to S because the lowest priority group is coming. The H is coming forward. So we reverse it, correct? Yeah. What's the problem? Clock moves this way. Okay, next one, diastereomers, that's it. Not epimers, because two things have changed. What if this one was bolded? That is bold dash dash here. That'd be an antimers, right? Okay, but that ain't not. Erythro, yeah. Both halogens on the left, when the methyl's at the top, methyl at the bottom, yeah? Now, we're going to have to learn how to rotate these. There will be a couple of examples where you have to rotate your Fisher projections. But, so this one didn't require you to rotate. How we do? Yeah?
I put chlorine on the right, but I was standing on the other side.
If you're standing over here, the ethyl is coming towards you.
Okay.
This means it's going away. With the ethyl going away, the chlorine's on the left.
Okay.
Because for it to be going away, I stood over here. The ethyl is going away. I'm over here. The chlorine's coming towards you guys. I'm bolded. That's my left. It is erythro, correct?
And assuming you're given partial since you said you drew. So if you drew it incorrectly, but then...
Yeah, if you drew 3O and called it 3O, I'll give you credit for calling your structure 3O. I want to, yeah, what you drew. 4, yeah, how do we do? We got a chiral carbon here, so you have potential for R and S. You also have one stereogenic alkene, you have potential for E or Z. Not stereogenic, not stereogenic.
Wait, can you say that one more time?
What's the question?
Can you like explain it one more time? Or like just go over which one you said. You just kind of pointed at it.
Chiral and stereogenic. Two stereogenic sites, 2 to the 2 is 4. What was your answer? Not that?
Yeah, I haven't accidentally added one more.
Which other? So you had 3 stereogenic sites? What was the third one?
I think the carbon on top of the, the carbon on top of the phenol group, I guess. No, down, right there. But is it because it's bonded to 2 carbons? Like directly bonded?
Because I got it wrong.
Oh.
Got that one there. Okay, I fell asleep here. There's actually, yeah, okay. There's here. Yeah. No!
Okay, so everybody should get that question right. How about that? We just all get it right.
Is the one on the other ring not stereogenic?
Where?
On the left ring?
Nothing there is stereogenic. Double bonds. Double bond in a 6-member ring is not stereogenic. It cannot be. These 2 bonds have to be cis on that double bond. They cannot be trans. If they're trans, you can't have a ring. Okay. I don't know why I got stuck on 2 there and just moved on. I think I fell asleep or something. Okay, so the answer is 16 there, yeah? The one on the far right is the most stable. It's going to get off the least heat when it's hydrogenated. Is that right? Most stable will give off the least heat. Contains the least energy. Yeah, most stable. That's the question. Down here, this is just a good old hydroboration oxidation. You give the anti-Makartnikov alcohol. Why did I say forget stereochemistry? Oh, there is no stereochemistry. No stereochemistry to consider that product, right? That's why I said forget stereochemistry. So you wouldn't be looking for something. Pretty straightforward alkene reaction. How we do?
Terrible.
Terrible.
No, I did. How'd y'all do?
Terrible.
Still probably is an A.
I can't wait.
Okay, I've been posted upstairs. Let's continue on with stereochemistry. What about page?
They're like 7:45.
Any questions at the very top? Don't do any of those. Any questions? How about Crestor? How many carbons in Crestor? Do you have an answer?
2.
2 carbons, yeah?
There's also that out.
That's all I see. How many stereoisomers possible for Crestor?
8. Because of the alkene.
Now we have to other things. It's more than just carbons. We also have this stereogenic alkene here. None of the others are stereogenic. I've got 3 stereogenic sites, 2 carbons and a stereogenic alkene. So this would be 8 for this answer here. Right? 2 to the 3 is 8. Could you draw 8? I think you could, hopefully. Zocor, how many carbons?
6.
Just read your answer. What would you get?
6.
6? 6 carbons?
7.
1, 2, 3, 4, 5, 6.
That was a 7. There's a 7 in that.
That one there's Carl. 7. Any others? No. I think I see 7. Is that right? Any other stereogenic sites? The only other type we know is an alkene, or the alkene stereogenic. No, alkene in a 6-member ring is not stereogenic. It looks like 7. 2 to the 7. Let me calculate it on that one. What is it? 40 something? 100? What is it?
120.
126?
28.
128. 128. Could you draw them all?
No.
You could. It would just take a weekend. Here's one of them. One of them is where all your stereogenic carbons, all your carbons are R. Just one. Then you have the enantiomer of that, which would be what? R would be S. Well, that's 2 of the 128. Okay. 2 to the 7 equals 128, I think. I was told it was 128. Over here, how do we do? RS. RS.
R.
R. I'm going to draw this in a fissure real quick because it's easier for me to look at it in a fissure. Because the H is not in the H is in the plane, so you can't just reverse it. That's only if it's forward. Real quick fissure. Yeah. F here, H here. BR is on which side? BR and the SH. Now I can look at it because now the H is going back. What is it, 1? What's higher atomic number, S or F? I think it's S, right? 1, 2, 3 is counterclockwise, H going back. S, correct? Yeah?
No.
I get it right? Yeah. Counterclockwise, H is going back, right? Okay. How might you separate the two enantiomers of this compound? That's the last page, I think, in the handout. Please be looking at that. We'll go over that at some point. How do you separate enantiomers? Can you just separate them by recrystallization and expect one enantiomer to crystallize and the other one not? No, you can't really expect that. They both have the same solubility. They have the same physical characteristics. The only thing they differ is rotating pp light. That's just kind of a quirk of physics. So why would one crystallize and the other one not? Diastereomers you can separate by recrystallization, as long as you're not just unlucky. But potentially they can. I mean, they're different, have different properties. Diastereomers do, but enantiomers. We'll look at that. Okay, back down where we left off at. Lots of good questions in that DQ page. I sent you the key, but if you have any questions about that, please ask. Okay, where did we leave off at? We do this one, I see a mirror plane there. That compound doesn't even have chiral carbons. That's not chiral. I would just call that one achiral, yeah? This one, what do we call this one? Anything? What do you see right here? Mirror plane. Methyl forward mirroring a methyl forward. Half a bromine back mirroring a half a bromine back. You see that mirror plane? Now it does have chiral carbons. How many chiral carbons? 2. That's chiral and that's chiral. Is that carbon chiral? Actually no, because if you go this way and this way, it's the same. So it's a chiral compound, but it's not chiral as a whole because it has a mirror plane. What do we want to call it? Meso. Meso. What is this over here? R or S? Let's see. Carbon with just H's, carbon with another carbon, or carbon with bromine. Carbon with bromine is going to be 1. Carbon with another carbon is going to be 2. Carbon with just H's is 3. Counterclockwise, H in the back. What is this? S? Okay, what is that one over there?
R.
Yes, R. How'd you know?
They have to cancel each other.
Because we see there's a mirror plane. This side is mirroring that side. If this is S, the mirror of S is R. Bet you a steak dinner, the other one's R. I've never lost a steak dinner. You see what the mirror plane can tell you about compounds? Right? If it's a mirror plane, what does a mirror plane mean? It means one side's mirroring the other. It's like a mirror there. Internal mirror. Okay, let's look at this. These are 5-membered rings. You see the 5-membered ring? It's just turned. Instead of like this, it's sort of turned like that and laid flat with this point now coming towards you. Sometimes you may see these like that. It's got 2 bromines. They're both sort of up. You can also draw these straight down. That's how you draw the difference. So these are cis. Those bromines are both cis. Were we able to find a mirror plane or no?
Yes.
Yeah, the mirror plane is coming sort of right through here. Now you have to kind of practice with looking at those. You can also redraw it. That is, draw it instead of a point forward, how about just a bond forward? And it's a 5-membered ring. Yeah? And then 2 bromines, cis. If we draw it like this, now you can more readily see that same mirror plane, which I tried to indicate over there. Sometimes just a redrawing can help. See it here easily? Mirror plane. Now both of these carbons are chiral. So what do you want to call this? It's a meso compound. Which means what? The mirror image is actually the same thing. There's no enantiomers. Is this compound going to be optically active? Will it rotate pp light? No, only chiral compounds rotate pp light. Non-chiral compounds do not. A meso compound is non-chiral. It just gets a special name because it has chiral carbons. Okay, mirror plane here. These are trans in a 1,3. Well, if I do one like this, 1, 2, 3. Well, if they were cis, 1,3 would be a mirror plane, but they're trans, right? So the other one is kind of like this. Now this ring is supposed to be kind of flat. If the ring is flat, we can have a bromine straight up and a bromine straight down. But that's, hopefully you kind of see it. Is that a mirror plane? Not with this down like this. Again, if it was up, it's not a mirror plane. This compound has no mirror plane. What does that tell us about the mirror image? It's different. Compound without a mirror plane is known as chiral. Because the mirror image is going to be different, just like my hand. Mirror image is different. This is chiral.
I feel like you have your bromines on the wrong carbons that you drew.
If that's 1, the next one's on the 3. If that's 1, the next one's on the 3.
But it should be the other way around. Like, you see what I'm saying? You have 1 at the base of the pentagon and then 1.
Okay, well you make a good point. I actually drew the enantiomer.
Okay.
This is the enantiomer. But we can look at either because, yeah, you're right. Since I put the point up, yeah. Because if you call this 1 and 1, if you do RS there, it's going to be different here. Yes. That is the enantiomer. But I can still get the answer I'm looking for.
Okay.
Because the enantiomer is still 1,3 trans. Good point. Yes. Okay, so there's a little bit of practice on finding Waldo. Okay, down below, alkene reactions. And there's a variety that we sort of skipped along the way inside the alkene handout. We'll do a couple here. Please be going back and look at those that we skipped. Okay, here we go. Sort of pulling it all together. Alkene. What does this do to an alkene? How you make the